Greetings. So, we discussed the semi-empirical laws of classical electrodynamics, and we recognize that the principle of superposition holds. This is a slide which shows some details. It is nothing but the principle of superposition that we have already discussed in the previous class. Intensity being a force per unit charge, it is additive, and the source can be an extended source, in which case you have to carry out integration instead of a discrete sum. And the integration will have to be over a line charge. If the source of charge is distributed along a line, that line need not be a straight line, it may have any kind of shape, it may bend, right, but it is essentially a linear charge. Okay. The line may even bend up and down and forward and backward, but it is still a one-dimensional charge, okay, although it may bend in 3 dimensions. It is still a linear charge, in which case you have to carry out the integration over the complete line, all right, or it may be over a surface, in which case you have to carry out a surface integration. So, you have got a surface charge density sigma at the source point r prime, okay, but this surface charge density may or may not be uniform. In general, it may not be uniform. In some special cases, it may be uniform, or it may be spread over a volume. Again, the volume charge density may or may not be uniform, but the source of electrical charge may be distributed either along a line or along a surface. This surface again need not be flat, it can be curved, it can be bent, so that it is shown as a curved surface over here, but it is still a 2-dimensional region. So, the integration has to be carried out only over 2 parameters, whereas in a volume integration it has to be carried along 3 dimensions. The linear charge, again, like I said, can be bent up, down, forward, backward. So, the line charge may spread over all the 3 dimensions, but it is still a linear charge. It is a wire along which the charge is distributed. Okay. So, essentially we have not stated anything that we have not known from the laws of mechanics, that the forces are additive. So, this is a force per unit charge and you have to add it up. So, we will take some examples over here just to become familiar with this. I assume that you have already worked out these and similar problems in your earlier courses. So, I will not spend too much time on this, but this is like a quick refreshing what you have learned in your previous courses. Okay. So, suppose you have got a uniform linear charge density and this charge density is lambda. So, there is lambda amount of charge per unit length along a straight line segment. The line segment has a length minus L to plus L, and you can ask what will be the field at a distance z above it. So, you just have to determine the field strength at this point due to a tiny charge element over here, and this charge element is going to be the charge density multiplied by the length of that segment. That will give you the total charge, and then you find what is the intensity at the point P, and then integrate over the entire length of the charge. So, the physics is very straightforward, the mathematics is very easy, okay? But it is a good idea to recapitulate some of these things that I am sure you have studied earlier. So, the horizontal components cancel because of symmetry, and the vertical components will add up to give you a net intensity along the EZ direction which is from bottom to the top in this, right. Assuming that this is a positive charge, otherwise it will be attractive and the direction will be just the opposite. And the net field due to the pair of lines. So, you take two symmetric points, okay, here and here, and then simply integrate over the region. So, the rest of it is straightforward geometry and a simple one-dimensional integral. So, once you evaluate this integration, you can find that it is you of course have this proportionality involving the permittivity of free space and 1 over 4 pi, and then you have this twice lambda L over z into root of z square plus L square, which in the limit z much smaller than L, or if L goes to infinity, you can get a limiting value, because when you ignore z, then in the denominator z square plus L square can be replaced just by root of L square, and that cancels the L in the numerator. So, that gives you a simple expression. You can also use the same technique to evaluate the field point, not at a symmetric point from the line, but an asymmetric point. In the previous example, we had the point right in the middle of the wire, but now if it is not in the middle of the wire, then this field point subtends an angle which is alpha at this point, all right, alpha 1, and at another point over here it submits alpha 2, right. So, from so these are the angles that it subtends, and you can rewrite the distance, because eventually the only physics that is going into it is the inverse square law. So, you just have to express these distances in terms of the appropriate lengths. Okay. The rest of it is elementary geometry. Okay. So, you have these terms when you must integrate over the region x equal to minus L to x equal to plus L, which is the length over which the charge is distributed. You can write it in terms of the angles xi or the angle alpha. Alpha is the angles subtended at the point P, and using similar straightforward geometry, you can evaluate these integrals. The integral of course has to be shifted from integration over the variable x to integration over the angle alpha. So, you find alpha in terms of x. So, we use this L1 minus x equal to h tan alpha relation, and using this you carry out the integration over alpha over the angle and determine the electric intensity at a given point. Okay. So, you can carry out these integration in a fairly straightforward manner. All you have to do is to use the inverse square law and use the geometry, and depending on the mathematical formulation of the problem, you can carry out the integration. The fundamental integration is over the variable x, because the charge is distributed over x, right. But if you consider charge segments in different regions, then the angle subtended by the field point at these charge segments changes. It is an extreme angle over here, and it sorts of changes as you go from left to right along the charge distribution. So, that is what makes it possible to change the integration over x to integration over the angle alpha. Okay. So, the mathematics is straightforward, but it is important to keep track of the physics that is going into it, because fundamentally you are simply using the Coulomb's law. You can have a circular line charge. Okay, so you have got a circular line charge in a flat plane, and you can ask what is the electric intensity it generates at a point P, which is on the axis through the center of the circle perpendicular to the plane of the circle. Essentially, you see the Coulomb's law written up, okay, which gives you the intensity of the field. You have to integrate over each charge segment, but because the charge segment is at different locations along the circular path, this integration over the circular path is expressed as integration over the azimuthal angle phi, and you can evaluate this integration quite easily. You see that this intensity will be 0 in the plane of the circle itself, because opposite elements will exert opposite charges at the center. Okay? Whether they are attractive or repulsive will depend on whether the charges are positive or negative, right? Whether they are like or unlike. But then as you move away from the surface, then it will have a component which is orthogonal to the plane of the charge circle itself. Okay? And then you can determine limiting values, what happens if you go sufficiently far from this where the circular charge is placed. So, in the limit that you are far away, then this circle really does not matter. It would be as if all of it is concentrated at a particular point. If you are sufficiently far away, then this small distance does not matter. You can carry out a similar exercise if you are using not just a circular line charge, but a line charge, but a charge which is along a flat plate. So, now you have got a surface charge, and you can determine the field due to a tiny element of the surface and then integrate over the whole surface. Or another way of doing it is to determine the effect due to a radial charge distribution, right, and then think about these different circles from the center expanding outward till it fills up the whole flat disk. So, you can carry this out as an integration over this or an integration over the surface. So, if you we will use this line charge because we just did it in the previous example. So, if you take the line charge, then it is over this particular segment. This segment arc length is rho delta phi. So, delta q by rho delta phi is the linear charge density along this arc, and this you can see is nothing but the surface charge density multiplied by delta rho. Okay, because you can divide and subtract, divide and multiply by delta A, and delta q by delta A will give you the surface charge density, which is what is given in the problem, and then you see that you get surface charge density multiplied by this delta rho. And now you can express the once you have the linear charge density lambda 0 in terms of the sigma 0 delta rho, then using the result of the previous example, you find what is the intensity at that point due to this circular loop, and then integrate this result as the radius of this loop goes from 0 to the radius of the flat disk, which is capital R. Okay. So, rho is the radial parameter, this is the radial coordinate in the plane polar coordinate system, and you carry out this integration. But as I mentioned earlier, you can certainly carry out the integration over the surface if you wish. So, this is the Coulomb's law. The 1 over r square is the gradient of the 1 over distance. okay, it is the negative gradient, force is the negative gradient of the potential. So, you recognize the potential over here, and you have the Coulomb-Gauss law, which is subsequently carried into the Maxwell scheme of equations, and it appears as one of the Maxwell's equations. So, it can also be called as the Coulomb-Gauss Maxwell law. And if you write the electric field in terms of the gradient of the potential, which is actually the negative gradient of the potential, it being a conservative field, then you get a second order differential equation in homogeneous equation, which is the Poinsot equation. And you can solve the Poinsot equation with appropriate boundary conditions, or if the charge density is 0, you get the Laplace equation, which also you can of course solve using appropriate boundary conditions. So the mathematics is that of solving differential equations with appropriate boundary conditions. Okay? And you can get the solution once you have the boundary conditions. Without the boundary conditions, you get nothing. So the important thing is to keep track of the Dirac delta in the Coulomb-Gauss law, because at r equal to 0 you have a singularity, okay? And the potential you can write in terms of the Coulomb potential is just the sum of the potentials generated by different charges. But if these different charges are distributed continuously, then you have to carry out an integration. So this is the integration. So the over the source region, so the sources are denoted by the primed variable and the field point by the unprimed variable. So that is just a matter of notation, but it is important to keep track of what is what. So this is the potential at the field point, and that it is now a sum of the total potential generated at the field point due to a charge at the source point r prime. It goes as charge over distance, which is the inverse distance potential, integrated over the entire source region. Okay? And then from the Coulomb-Gauss law you get this relation, but now you have got the Laplacian, which is del dot del, operating on this 1 over distance. Now mind you, this is the gradient operator. It takes the derivatives with respect to distance, right? Distance of what? It is taking the gradient with respect to the field point. The integration is over the source region. Okay? So I can move the source anywhere and think of the influence at the same point. Okay? Or I can keep the source fixed and move the field points. So these two are completely independent operations. Differentiation with respect to the field point and integration with respect to the source point are completely independent. So the del dot del operator, which is outside the integration, marches right into the under the integration sign, and then you have to take the del dot del, which is the Laplacian operating on 1 over distance, which is determined by the modulus of the position vectors r and r prime, which are respectively the field points and the source points. So the Laplacian operating on 1 over distance is again in terms of the Dirac delta. And when you carry out this integration with the Dirac delta, only the value of the other factor in the integrand at r equal to r prime survives, or rather the r prime equal to r survives, all the other make 0 contribution, and you recover the Coulomb-Gauss law without any problem. Okay? So notice that this is very simple, but the Dirac delta integration plays a fundamental and important role. So we can also determine the potential of a uniformly charged solid sphere. Okay, now you have a solid sphere. So, we are letting our geometry become a little more complex, and then of course, it can go from line to flat spaces to curved shades, and then to spheres, and then to volume regions which have some arbitrary and crooked shape, even ugly looking shape does not matter. You can do it using the same integration procedure. So, if the field point is very far away from the source region, then the shape of the source and so on really does not matter. Okay? But if it is not so far, then you have to take into consideration, and for regions which are less than r, this is a spherical charge distribution. So, for the spherical charge distribution, the total charge is what you have to calculate. Now, inside the sphere, if you find what is the intensity at a point inside the sphere, then at that point you have got some charge in the interior region and also some charge in the exterior region. The charge on the exterior region will not exert any force inside it. There will be a potential, but not a force, because the only charge which is contributed to the intensity is the charge which is enclosed, which is the statement of the Coulomb-Gauss law. If you use the spherical surface, the Gaussian surface, then it gives you the total charge which is encapsulated by the Gaussian surface. So, you have to determine what is the total charge which is encapsulated. And once you have the intensity, you can also find what is the potential at that point. How would you get it? Because the potential at that point will be the energy stored in it by doing work in bringing a charge from where it is 0. So, that will be infinite distance, because at infinite distance physical quantities will not exercise any influence, and from there you determine what is the work done, and this amount of work done will not get lost because of conservation of energy, right. So, it will get stored, and that will be the potential at that point. So, you have to integrate the force into distance, which is the force per unit charge into distance, which is E into delta r, and integrate this, add it up all the way from infinity to r. So, when you carry out this integration, you can, it is a very simple straightforward integration over one variable, and you can find what is the potential at a given point inside this, right. So, outside this spherical region, it is even simpler, it is q over r, right, for exactly the same reason, and you can sketch it as a function of distance from the center. So, outside for r greater than r, it is q over r, so it goes like this, and inside for distances less than the radius of the sphere, it goes as this expression that we have just evaluated. So, we can sketch this very nicely. Okay. So, this is the potential of a uniformly charged solid sphere. What if the sphere is hollow? Then it has got a certain total charge which is spread along the surface. There is no charge inside and no charge outside, it is just in a infinitesimal sheet which is closed on itself in a spherical shape. And using the same logic, you can find what will be the intensity at points r which are outside the sphere. So, this is the total charge you have to calculate, which will be the charge over a tiny surface element integrated over the entire surface, which is 4 pi r square, right. And just above the surface you can calculate what it is, and you notice that it will be sigma over epsilon 0 just outside the surface, because just outside the surface the small r and the capital R are practically equal. So, they cancel, the 4 pi's cancel, and you get sigma over epsilon 0. Inside the surface, the intensity will be 0, because what is the charge enclosed? There is no charge inside. And this is not surprising. Here we have arrived at this conclusion using the Coulomb-Gauss law, but using the Coulomb's law itself, you can see that if you look at a point inside a spherical region, then there are forces from opposite sides which have opposite directions. But then if you draw these cones passing through the center, then you have the area of the surface which increases with distance square actually. R square d omega is a surface element on the surface of a sphere. D omega is the solid angle subtended by a patch on the surface at the center. Okay. So, that surface element is r square d omega, and the force itself goes as 1 over r square. So, they nicely cancel each other. So, the force exerted inside goes to 0. Okay. So, whether we use the Coulomb's law or the Gauss's law, they are the same. What about the potential? So, we have seen that the force is 0, but the force is the gradient of the potential. It does not mean that the potential itself is 0. The gradient of the potential is 0. It means that the potential is not changing inside, but it can have a non-zero value. Okay, it cannot change. So, it will have the value that it will pick at the edge, and that value will remain unchanged inside. Okay. So, this is the value of the potential inside the region. These are constants, both the numerator and the denominator are constants. Q is the total charge. Outside it goes as Q over R, inside it goes as Q over a fixed distance, which is the radius of the shell. What about the electric field of a line charge distribution? So, I will just discuss a few examples so that you are comfortable in applying the Coulomb-Gauss law. If you have a linear charge density, you can think of a Gaussian pillbox, and Gauss's law can be used best if you can exploit symmetry. It does not mean that it does not hold when there is no symmetry, it holds. We have just discussed that, all right. But it becomes extremely useful when you have a symmetry. So, you construct a symmetric Gaussian surface. So, that will obviously be a cylinder around this linear charge distribution, and then you evaluate the Gaussian surface integral E dot ds, and there are these the closed surface is now the two flat faces of the cylinder and then the curved face. But the two flat faces will have a unit normal which is pointing one way at one face and the other way exactly the opposite way, and by symmetry these contributions will be equal but in opposite directions, all right. So, the E dot ds term on these faces will cancel each other, and you just have the integration over the curved face. You carry out that integration, and that is over rho and phi, okay. And that is now a straight that is over z and phi. So, that at a particular radial distance from the axis, which in the cylindrical polar coordinate system is the distance rho. Phi is the azimuthal angle, and you carry out this integration and you get the expression for the intensity. This is independent of length. What about the electric intensity inside the cylinder? If the cylinder is not just a slim wire, but if it has got a certain cross section, okay, it has got some thickness, then outside the wire it will change according to the previous law, but inside, if you construct these Gaussian pillboxes, okay, then depending on how much of the charge you accommodate, you will have a different intensity, because the Gauss's law tells you that only as much charge would contribute as is included inside the closed surface over which the Gaussian surface integral is carried out. So, if you carry out a surface integration over a Gaussian pillbox which only extends up to a certain intermediate point, it does not go outside the size of the cylindrical charge itself, but somewhere inside, then only as much charge is to be included. So, the integration over the charge density, the charge that is enclosed is nothing but the integration of the charge density, and assuming that it is uniformly it is charged, the charge density is not uniform, but it changes as you go away from the axis, and it changes linearly. Ks prime is the linear dependence of the charge density. So, if you carry that out, you get this expression, and now it is a matter of using the Coulomb-Gauss law and the corresponding surface integrals. So, you have determined the total charge up to a radial distance away from the axis up to S. So, that goes as the cube of S. What about the surface integral E dot ds itself? So, E dot ds again you calculate using the same kind of thing, construct a Gaussian pillbox, you have got a left face and a right face which have got normals in the opposite direction. So, those contributions cancel, and then you have got the integration over the curved surface. So, that is over Z and it is over phi, the azimuthal angle. So, over the azimuthal angle it will give a factor of 2 pi, and over Z it will give you the length of the segment over which you are considering the pillbox. Okay? So, that is the length L. So, that gives you twice pi Ls times E rho. So, you had the cube of S in the charge, and on the surface integral you have got 1 power of S. So, 1 power of S cancels 1 power of S over here, and E goes as Ks square by thrice epsilon 0. Okay? So, it seems to increase as you go away from the axis, but of course, it cannot keep growing increasingly, because the charge is not going to grow continuously. The charge will, the increase in charge will stop once you meet the boundary of the cylinder, and then it will start diminishing. Okay? So, this is independent of L. So, it increases with distance quadratically as the square of S, but only till you hit the boundary, not outside. What about the electric field intensity on either side of an infinite charge sheet? So, you have got a charge sheet which is flat, it is thin, all right, and you are asking what is the intensity above the charge sheet and below the charge sheet. So, it is infinite. So, you construct a Gaussian pillbox. So, it will contain a finite charge element, okay, because the radius of the cylinder of the Gaussian pillbox is finite, right. So, that depends on the surface charge density times the cross sectional that you have intersected by this Gaussian pillbox, which is sigma into delta S. And then there will be on the top and at the bottom, and both will be equal because of symmetry. So, they add up, okay. They will be exactly the same effect adding up, and then you can see that the intensity will be sigma over twice epsilon 0, and it does not depend on how far from the charge sheet you are looking at. That result should not surprise you, because what is any distance above the sheet if the sheet itself is infinite? No matter how far from the sheet you look at, it is no distance compared to the size of the sheet. So, this is an infinite sheet. So, it becomes completely independent of Z. Okay. What if you have a uniformly charged sphere? Then again you can evaluate the problems using similar Gaussian integrals, evaluate the total charge which is enclosed. And now we talk briefly about the work done, which we did earlier in the discussion on the potential, but now we will generalize it to more general charge distributions. So, when you bring another charge from infinity to a certain point, you are doing work on that, and that energy is going to be stored in the system, which is the potential at that point. Now, you have to work with potentials. If you look at this equation, the intensity is the negative gradient of the potential. Now, when you use the Lorentz force law, you are going to use the intensity. What is the force acting on a charge? Charge times E plus V cross B, right. So, you need the electric fields E and B to determine this, and once you have the force, you can write F equal to dP by dt, integrate it, put the initial conditions and get the solution. All right. Now, you have introduced potentials, and the gradient of the potential gives you the intensity. So, is it just for fun that you are doing this calculus, that okay, you take the derivative and get the intensity, or you can carry or do some integrations, and then if you integrate E dot dr, you can determine what is the potential. Okay. So, certainly this is nice and easy mathematics, but it will turn out that because it is the gradient of the potential, the gradient of a constant is always 0. So, you can add or subtract any constant to this and the intensity will not change. So, this is what is called as gauge transformations. You can go from one set of potentials to another set of potentials, but still get the same fields, and that gives you a feeling that okay, the potentials are not important, it is the fields that are important. But as we will discuss as this course develops, and we in fact when we get into quantum mechanics, we will talk about the potentials, and we will find that they have an important effect. Even if the field is 0, they will have a measurable effect. So, the potentials become more important in our analysis. So, now we have written the intensity as a gradient of a potential. So, you can also write it as a quantity whose curl is identically 0, because the curl of a gradient is always 0. And the curl of E being 0 and E being the negative gradient of potential can be considered to be equivalent expressions of the conservation of energy, right. But the criterion of the conservation of energy is not just this. The fundamental criterion is that the work done over a closed path goes to 0, or the work done over an arbitrary path is independent of the path. So, those are the fundamental criteria and not these. These are like secondary derived paths, derived expressions of the conservation principle. So, you can apply this to point charges. You can have you can ask what will be the potential of a distribution of point charges, because every time you bring one charge from infinity, you do work on it in bringing it here and placing it here. That work is going to be available in the system. Now you bring one more charge, you bring a third charge. So, all that is going to be added up, and while adding it up, you have to keep track of whether you are bringing a positive charge or a negative charge, because the signs will be different. Okay? So, the work done is F dot dl integrated from point A to point B, over which you move this charge. The force is the charge times the intensity. Okay? And you can evaluate this work done, and you get the potential difference between 2 points, and you can allow one of these points to go to infinity where you consider the potential to be 0, and that allows you to determine an absolute value of a potential at a given field point. So, if you are now assembling a number of charges, and these are discrete charges, then you have to add them up, keeping track of the sign, because the work done on positive charge and negative charge will be exactly opposite. Okay? So, to get the first charge, you do not have to do any work, because work has to be done against what? There is nothing there. For the second charge, you have to do this work, which will be q1, q2 over distance, right. For the third charge, you have to add up these two. Again, we are using the principle of superposition. So, you will have the charge q3 over 4 epsilon 0 multiplying q over r31 plus q2 over r32. These charges may have different values. So, you can add it up, and you can write this total work done as a sum of work done between pairs, but when you take the pair j and k, when k is equal to j, the work done is 0, because you do not do any work to bring a charge against itself. Okay? So, wjj is 0, otherwise it is qj qk over the distance between j and k, scaled by the 1 over 4 pi epsilon 0, and you can now add it up for n charges. You can write this in terms of a matrix W, which is obviously a symmetric matrix with diagonal elements being 0, okay, because we have already discussed that qjj is always 0 for every value of j. So, the transpose is equal to the matrix itself, and you can write the potential energy of the charge distribution by summing up these pairs of work done. So, to avoid double counting, you have a factor of half, and you can let j and k both go from 0 to n, the number of charges. What happens when k is equal to j? It does not matter, because wjj or wkk, whenever the two indices of w are the same, it contributes 0. So, it does not give anything to this. But when you write this in terms of the Coulomb potential and sum it over, then you must avoid j equal to k, because otherwise 1 over rjk for j equal to k becomes 0, and then you will have an infinity. So, when you write it in terms of the charges over distance in that form, you must write this prime or some indication, somewhere you must say that k equal to j must be avoided. So, here you have written it as half of j going from 1 to n, k equal to 1 to n, 1 over r j k, but j not equal to k. If you write it in terms of the work done, you need not be careful about saying j not equal to k, because j already goes to 0. And this is the work done in assembling the system, and it will be stored over there. So, this we considered discrete charges. You can write it in terms of the potentials at that point, and you can write the potential either as phi or as v. So, these are two equivalent notations. I prefer to use a different phi for this and a different font phi for the azimuthal angle, and you can write it in terms of either the potentials or the Coulomb Qj Qk over Rjk, but if you write that, then you must make sure that j equal to k is not included. So, either you write it explicitly in your summation index or put a prime, or some kind of a reminder, you have to flag it that okay, you cannot include j equal to phi k. What if you have a continuous charge distribution? Okay, so here you have a charge distribution, some of it is positive, some of it is negative, and it has got some arbitrary shape. Then you have to come up with a similar expression, but then you have to integrate over the charge densities over the entire region. So, you will have a volume charge density. So, you have a volume integral and a surface integral. Okay? And this integration must be carried out over the entire space. You cannot rule it out, okay? Because if there is a charge density which is in some part of space, and you evaluate the potential at this point by integrating this, you do not get the potential at this point if you forgot to include the contribution from some charge in some other part of space. So, the volume integration has to be over the entire infinite space. The surface integral also has to be over the entire infinite space. Okay? It has to include all the space that is there in the universe. Okay? No other source of potential must be present in the region, right? Everything is to be included. So, once you do that, then the contribution from the surface integral would vanish. Okay? And then you have to work with only the volume integral. And now you know from the Coulomb-Gauss law that we have discussed earlier that rho is nothing but the divergence of the electric intensity scaled by the factor epsilon 0. So, you can write this divergence of E in terms of the divergence of phi times E, because this is just the divergence of a product phi times E. So, using this identity, you can write this divergence of E as a difference of these two integrals, of which this is the volume integral of the divergence. Okay, this is the volume integral of the divergence, and so there are these two terms. So, this volume integral of the divergence is equal to the surface integral over here, and this surface integral will go to 0, because where is this surface? This is surface at infinity. Okay. So, that contribution at infinity will go to 0, and then you are left with only the volume integral E dot E. So, the energy density is E square by 2 times epsilon 0. You are integrating E square over 2 times epsilon 0 over the whole space. So, that is the energy density. So, this is where we stop today, and I will continue from this point in the next class. The important thing to remember is that the volume integration must be over the entire space. It is not over a subset of that, and that is a point which students tend to forget sometimes. So, make sure that you are carrying out the volume integration over the entire space, because only then will the corresponding surface integral vanish. So, if there are any questions I can take, otherwise we are done for today, and then we will continue from here next time.
We do gauge transformation.
Yes.
For one field we can have different constructions of potentials.
Yes.
Which essentially tells that potential is not unique.
Yes.
And we can have potentials without fields. Basically. So my question is that is field base more fundamental or potential more fundamental?
As you get into quantum mechanics, the potential becomes more important. See, the fields are involved in forces, okay, in the Lorentz force. The Lorentz force is Q times E plus V cross B, and E and B come explicitly in the force expression. But the idea of force is dispensed with in quantum mechanics. In quantum mechanics, you are working with solutions to the Schrodinger equation. You construct the Hamiltonian as you first construct the Lagrangian, and then carry out the transformations to Q and P, construct the Hamiltonian, and then you quantize it. So, you have started out with the Lagrangian, which includes, and what is the Lagrangian? It is T minus V. So, you are working with the potentials, you are not working with forces. So, the potentials become more important down the road, okay, rather than the fields. So, you get an impression from classical electrodynamics that the fields are important and the potentials can be done away with. That is not true. You also get a feeling that the potentials are not really measurable, but we will discuss in our once we get into the part on quantum mechanics that the effect of the potential can actually be measured. It impacts, it has a physical impact which is detectable. You can perform an interference experiment with electron guns, see the interference pattern, and then have vector potentials in that region, and you will see that it will have an effect on the path which the electron takes, which will affect the interference pattern. So, that is the Aharonov-Bohm effect. We will discuss it a little later in this course. So, thank you very much.